Chapter 3 Torsion Homework Solutions 3.1 Problem 3.1 We have a electrical motor. Apply a torque of 2.5 kilonewton meter. Apply torque of 2.8 kilonewton meter on shaft EF at E. Knowing each shaft section, each of these are solid. Based on the additional torques as depicted, we have TF here at 1.6 kilonewton meter, TG here 0.8 kilonewton meter, TH here 0.4 kilonewton meter. Note that the applied torque going this way, while the rest TF, TG, TH going the other way. So the net is balanced. 2.8 going one way, and 1.6 plus 0.8 is 2.4 plus another 0.4 is 2.8 going the other way. So based on statics, it's balanced. Based on the additional torques as depicted, please determine the maximum shearing stress. We're going to use the maximum shearing stress equation, Tc over J, in shaft EF from here to here, with radius of 25 mm, shaft FG from here to here, 23 mm radius, and the last shaft GH from here to here, radius of 21 mm. So for EF, the net internal torque between E and F would be based on statics, would just be 2.8, because if you make the cut here, the internal torque generated has to balance the applied torque, and that will be 2.8. So the equation that we're going to use simple is tau max for EF section would be Tc over J. And what is it? T? 2.8 kilonewton meter or 2,800 Newton meter. C, we said is 25 millimeter or 25 times 10 to the power of -3 meter. And J is half of pi r to the power of 4, half pi radius to the power of 4. And then you will be able to get the answer. So let's continue. Similarly, for section F and G, and then the first part is based on statics to determine the torque. The TFG, the net internal torque, would be, if you make the cut here, 2.8 goes one way, 1.6 goes the other way. To balance, we need an internal torque that is the difference. 2.8 minus 1.6 would be 1.2 kilonewton meter. So similarly, tau would be Tc over G. T would be in this case 1.2 kilonewton meter or 1200 Newton meter. C we said 25 millimeter, 23 millimeter, 21 millimeter. So this would be 23 millimeter or 23 times 10 to the power of -3 meter. J half pi radius to the power of 4, and you get the answer. Finally, for section GH, same. We must first determine the net internal torque TGH. You can go from the left, then it would be 2.8 goes one way, both 1.6 and 0.8 goes the other way. So 2.8 minus 1.6 minus 0.8 would be 0.4 kilonewton, goes the other way. Or you can just cut from the same location, but look from the right side. So you have 0.4 goes the other way. So to balance, the internal torque here will just be 0.4. Either way, you get the same answer. So tau is Tc over J. T would be 0.4 kilonewton meter or 400 Newton meter. C we said is 21 millimeter or 21 times 10 to the power of -3 meter. J is half pi, and then you get the answer. Homework 3.2. For this one, it looks complex. Let's explain it. A component with solid rod EF, a solid rod EF, and a hollow tube with flange. This tube with flange, GH, hollow tube with flange. They are welded onto a flat end plate. This flat end plate, we call it a GFI. Flat end plate, GFI. And the solid rod, the cylindrical rod EF, and the GH tube share the same longitudinal axis. They're concentric, as illustrated. Of course, we are only looking at the cross section. The hollow tube GH is fixed at the rigid, fixed by the flange onto A prime, B prime. So you have to imagine this: a solid rod in the center, a tube outside. The tube and the rod are together welded onto GFI, and the tube is fixed onto support A prime, B prime using bolts. Okay, so the EF rod has a diameter of 3.81 centimeter and made of steel with allowable shearing stress of 82.7 megapascal. So we know the material property, the diameter for this solid rod and its allowable shearing stress. Similarly, the tube GH is made of copper alloy with OD outside from here to the axis is 7.62 centimeter, and ID from inside to the center to the axis is 6.35 centimeter. And the allowable stress for this copper tube is lower at 48.3 megapascal. Okay, so we know the material property for the tube, for the rod, the geometric diameter for the tube, for the rod in the center, and then we want to determine the largest torque, external torque that can be T that can be applied at the E end. So A prime, B prime are fixed. So as you twist, apply a torque at E, you can imagine it's going to try to twist the rod. That's one. At the same time, because the rod is welded onto a solid plate, it will also try to rotate the GH tube. Of course, the assumption is assuming the welding is very strong and is not a concern for failure at all. So to do this, let's look at each of the sections. First, for solid rod EF. For solid rod EF, you are applying a torque and it's not the maximum shearing stress tau max would be Tc over J. C would be the radius for the rod EF, and J would be the moment of inertia axial for this rod. And this whole thing, Tc over J, has to be smaller than our so-called allowable shearing stress, 82.7 megapascal. Okay, then rearrange. You would have T would be equal or smaller than J times 82.7 megapascal divided by CEF. And then you plug in the number. Remember the axial moment inertia is half pi radius to the power of 4, but then you have a radius in the denominator, so as a result you have radius to the power of 3. And what's the radius? We said it's 3.81 centimeter, and you convert it into meter. Half pi radius to the power of 3 times this stress level 82.7 10 to the power 6 Newton per meter square. And in the end, you get a number in the unit of Newton times meter for the largest torque when you only consider the shearing stress for the EF rod. Okay, that's only the first part. For now, let's consider the GH tube. Of course, we said the bottom plate is strong enough, the welding is strong enough, so let's only consider GH tube. Similarly, we said that tau max is TC over J, and the C would be the maximum dimension for the tube, CGH, okay, and JGH would be the moment of inertia for this tube. And as a result, similarly, the maximum torque applied would be J times the allowable stress divided by C. And similar as before, but then we have to consider in this case, because it's a hollow tube, the J would be different. It would be half pi, but outer radius minus to the power 4 minus inner radius. And the outer radius would be outer diameter 7.62 centimeter divided by 2 to the power 4 minus inner diameter 6.35 centimeter divided by 2, then you get radius to the power of 4. That's the J term for this hollow tube times allowable stress. In the denominator, it would be our radius for the outer radius for the tube, which is 7.62 centimeter divided by 2. You plug in the number, you get another T value, allowable torque value in Newton times meter. And then the second value is considering the tube. Overall, we said the plate is strong, the bonding is strong, so we would only be able to apply a torque that is the smaller of the two. One is considering tube, one is considering the rod, and you get that value. Okay. Homework 3.3. Two solid shafts G, H, and I, J are connected by gears K and L as illustrated. So two shafts GH and IJ. GH is connected to gear K and IJ is connected to gear L, and the gears bite into each other, K and L. Okay. The radius for gear K is 4 inch. Radius for gear L is 2.5 inch, and both shafts GH and IJ are made of the same material steel with allowable shearing stress of 8 KSI, 8,000 PSI of allowable shearing stress for both GH and IJ shaft. The radius for the shaft are GH is 0.8 inch, IJ is 0.625 inch. So we know the geometry, we know the material property for the shaft, and then we want you to determine the largest torque that can apply at each side. Of course, we assume it's under kind of equilibrium. It is under equilibrium, either doesn't move or move at a uniform speed. Okay, can be applied at each end. You can imagine if the torque is too large, either one shaft will fail or the other one. And now that's what we want to determine. So let's first consider the simplest situation, which is only consider GH. For shaft GH, so what do we know? We know the allowable shearing stress is smaller than 8 KSI, which means tau max, shearing stress maximum, would be what we learned in chapter 3, TC over J should be smaller than 8,000 PSI, pound per square inch. And C would be, of course, the radius for the GH shaft J would be the moment of inertia, axial moment of inertia for the cross section of this shaft. So as a result, T would be J over C times 8,000 pound per square inch. And the J over C, that will be half pi J to the power of 4, C to the power of 1, so as a result to the power of 3. And then when you plug in the number, you get a torque value, certain pound times inch. Okay, that's only consider GH. Now let's consider for IJ shaft. For IJ shaft, okay, because of the two gear connection from K to L connection from statics, we wish you still remember the ratio between the torque for one. I probably should have torque K, which is the same as torque applied here, divided by torque L would be proportional to the radius Rk over Rl. The reason being the force of interaction is the same for K and L, so the torque would be the force times the distance from the force, which is just the radius. So as a result, the torque at K or transferred, which is essentially the torque applied at each side, would be Rk over Rl, the radius ratio for K over L times the TL. Okay? Or you plug in the number, radius for K gear is 4 inch, radius for L gear is 2.5, 4 over 2.5, that gives 1.6 times TL. So which means the torque applied at each side will be 1.6 times the torque experienced at L gear or at IJ. Then, similarly as before, we said for IJ shaft, the maximum shearing stress also has to be smaller than 8,000 psi or 8,000 pound per square inch. So tau max again would be Tc over J, and T in this case would be the net torque on L gear or the internal torque for IJ, which is the same, times Cij. Cij would be radius for the IJ shaft, and the Jij would be the moment of inertia for IJ shaft. Okay, and as a result, TL, the torque for L should be smaller than or equal to Jij divided by Cig times 8,000 pound per square inch. And then J over C would be half pi radius to the power of 3 times 8,000, and you get a number. And as a result, the T would be smaller, equal to 1.6 times TL, and we know it should be smaller than 1.6 times all this, and 1.6 half pi 0.625 inch to the power of 3 times 8,000, and you get a number. And as a result, overall, the maximum torque that can be applied would be the smaller of that two values. One consider GH and one consider IG, and you get that number. Okay? Homework 3.4. A motor applies a torque of 500 Newton meter on HGFE shaft, and the motor is rotating at a constant speed. Knowing the shear modulus G is 27 gigapascal. The shear modulus G is 27 gigapascal, and the torques on the pulleys G and F are shown. So the motor is applying a torque of 500 Newton meter, while the torque at the pulley G or gear G would be 300 Newton meter. Goes the other way. and the torque applied on pulley F would be 200 Newton meter goes the other way. So 500 Newton meter goes one way, 300 and 200 goes the other way. So overall, the shaft has balance of the total torque. Okay. Please calculate the angle of twist between F and G. So between F and G, and then between from here F and H. Knowing shaft radius FG, GF is 2.2 centimeter, 2.2 centimeter here, and between G and H, our HG is 2.4 centimeter. Between E and F is 2.0 centimeter. Okay, so that is our problem. We know the motor torque applied, we know the pulley torques, and it's balanced. We know the dimension, the length, the radius, and we want to know the angle of twist between here F and G and between F and H. Okay, so this is our problem. Let's first calculate between F and G, between F and G. So let's say between F and G, if we make a cut through here, what would be the so-called internal torque? Well, if we make the cut here on the pulley, that will be 200 Newton meter goes one way. So the net internal torque should also, to balance this torque, it would just be 200 Newton meter. That's one way to view it. The other way is if I cut it here, look from the left, 500 goes one way, 300 goes the other way. If we make the cut, we need another 200 to balance this 500. The internal torque would still be 200. So either way, looking from the left or from the right, you should get the internal torque at a arbitrary normal cross section between F and G would be just 200 Newton meter. So what about the angle of twist? We call it phi FG. The angle of twist from F to G, phi FG, from our equation we know is TLJG. T for torque, the larger the torque, the larger the angle of twist. L would be the distance, the length for the shaft between F and G. The longer the distance, the larger the angle of twist. That's natural. And J would be the moment of inertia for the shaft cross section, axial moment of inertia. And of course, the larger the moment of inertia, the smaller the angle of twist. And finally, G would be the shear modulus. The larger the shear modulus, the rigid the material is, the smaller the angle of twist. So let's plug in the number. TFG, we said internal torque is 200 Newton meter. L, as we given from F to G, is 1.2 meter. J, moment of inertia for the cross section is half pi radius to the power of 4. And what's the radius? We said is 2.2 centimeter or 0.022 meter, and times shear modulus G, we said is 27 giga, 27 10 to the power of 9 Pascal or Newton per meter square. And as a result, you get a number in radian or in degree. You can convert that one into degree, okay, if you want. You don't have to. Similarly, between G and H, between H and G. So if we make the arbitrary cut here, looking from the left, we have 500 goes one way. You must have a 500 going the other way to counteract this one. On the other hand, if we make the cut and look from the right-hand side, yes, 200 goes one way, 300 goes one way, combined 500 goes one way. So look from the right side, we also need 500 to balance it. So either way, we should get net internal torque at a arbitrary cross section between G and H would be 500 Newton meter. So similarly, phi would be TLJG. Of course, the T, L, J, G are all for between G, H. Torque, we said, is 500 Newton meter. L, as you see, 0.9 meter between G and H. J is half pi radius to the power of 4 and radius 2.4 centimeter or 0.024 meter, and J same, and you plug in the number, you get another value. Okay, and finally we know the angle of twist between F and G. The other part, for the B part, is we want the angle twist between from F and H. So you can just add it up because FG rotates one way, HG also rotates in the same way. So you just linearly add them together and you get the answer. Okay, either in degree or in radian. Homework 3.5. We have solid aluminum rod, and G shear modulus 26 gigapascal. It's bonded, the aluminum rod is bonded to a solid copper alloy rod. Copper rod, same radius or diameter, but the copper has shear modulus of 39 gigapascal. So the radius for both rods are 10 millimeter. Copper 10 millimeter diameter, radius 10 millimeter radius, aluminum 10 millimeter radius, and the copper rod and aluminum rod are strongly bonded together, and they are fixed at the D end. And you have torque applied at the free or F end. So we want you to calculate the angle of twist with respect to base D at point E, at the joint point, and at point F, the free end, respectively. So first, between D and E, the angle of twist between D and E would be just TLJG. And what is T? Well, if you make the arbitrary cut all the way to T, you find the T is just the same as the TF, or 50 Newton meter. Okay, L is from D to E is 0.2 meter, and J is the moment of inertia for the cylinder around its axis. It's half pi radius, which is 10 millimeter or 0.01 meter to the power of 4 times G. Shear modulus for copper would be 39 giga 10 to the power of 9 Newton per meter square. And if you plug in the number, you would get a certain radian, or you can convert that into degree. Okay, that's the first part. Then for the second part, between D and F, so we already know between D and E. We now need to know the angle of twist between E and F. So between E and F, the same equation phi, but for E and F would be T LJG, and L and J and G are all for the EF part. T, as you can imagine, would be the same. If you make the cut, it's consistent 15 Newton meter. And L from E to F is 0.4 meter. And J is half pi, but it has the same radius, 0.01 meter or 10 millimeter, times G for aluminum, we said is 26 giga 10 to the power of 9 Pascal or Newton per meter square. So meter square in the numerator, meter to the power 4, meter to the power minus 2, so cancel. And Newton cancel, and then you get the number in radian or degree. Finally, between the angle of twist for F side versus G, that will just be add up the phi dF, phi dE plus phi EF, and you get the answer. Okay. Homework 3.6. A 6 foot long, 6 foot long composite shaft. Composite shaft consists of a 0.2 inch thick copper shell. This pink colored, red colored copper shell with shear modulus of 5.6 times 10 to the power of 6 psi. This copper shell is bonded to a 1.2 inch diameter iron core. So the iron core is this gray colored solid piece, 1.2 inch in diameter, and the copper shell has thickness of 0.2 inch, and both of them are 6 foot long. Of course, we are not drawing to scale. The steel core has shear modulus of 11.2 times 10 to the power 6 psi, and the shear modulus for copper, we said it before, is 5.6 times 10 to the power 6 psi. Okay, so the shell and the core are strongly bonded together. It's a composite. We assume the bonding is very good between the iron or Fe core and the copper or Cu shell. If the shaft is subject to 5,000 pound-inch torque, a pair of torque, 5,000 pound-inch, we want you to calculate the maximum shearing stress in the steel core for the center steel core and the angle of twist of one end versus the other end. So this is a statically indeterminate problem. From statics point of view, the torque borne by the iron or Fe and the torque borne by the copper or Cu add up to the total torque, 5,000 pound-inch. So as you can imagine, the total torque is shouldered or borne or handled by two parts, some part by the iron or Fe, some part by the copper or the Cu. But the total torque for these two parts of the material combined to be 5,000 pound-inch. That's from statics. That's the only equation that we can get from statics. So from here, we cannot know how much is shouldered or borne fall onto the iron or Fe, how much of the torque fall onto copper. Then we have to, like any other statics indeterminate problem, we have to consider geometry or deformation. So consider geometry. We said it's a composite beam, strong bonding between the iron core and the copper shell. So as a result, essentially the angle of twist for the iron core or Fe core and the copper shell or Cu shell would be the same. So angle of twist, assume we are well within elastic limit. Then the angle of twist for both would be TLJG. T again would be the torque on that part of the composite. L would be the total length, and J would be the moment of inertia, axial moment of inertia for that part of the composite, and G would be the shear modulus for that material. So we can write each of them for the iron of Fe and for copper or Cu. And once we have this relationship, the lengths for copper and iron are the same. They got cancelled out, and as a result, the TCU, the torque on the copper part, would be, you move the J and the G to the numerator on the other side. JG for Cu divided by JG for iron or Fe times TFE. So that's an additional relationship once we consider geometry or deformation. Both the core and the shell, they would twist at the same angle because of the strong bonding between iron and copper at the interface. Okay, so now we have two equations, one here one here, and two variables. One is TFE, one is TCU. Okay, and in principle, the problem can be solved. If we plug in the number, TCU would be all this times TFE, and the JCU, the copper moment of inertia, would be half pi. Copper, remember, it's a hollow cylinder. It will be outer radius to the power 4 minus inner radius to the power 4. We said the iron, the solid iron core, is 1.2 inch in diameter. So the radius for the iron would be 0.6 inch, which means the ID for copper would also be 0.6 inch. And the outside radius for copper would be, as we view, the thickness is 0.2 plus half of the diameter for the iron core would be 1.2 divided by 2.6 plus 0.2 would be give us 0.8. So that gives us the J for copper. G for copper we said is 5.6 times 10 to the power 6 psi. Okay. And then for iron core, it's still the moment of inertia is half pi radius 1.6 divided by 2, which is 0.6, 1.2 divided by 2, which is 0.6 to the power 4 inch to the power 4 times G for iron, which we said is 11.2 times 10 to the power 6 psi. And if you plug in the number, you get the TCU would be 1.080 times TFE. Okay, so once we have this, we can put this into the equation above. TCU is 1.08 TFE. As a result, TFE would be total 5,000 pound-inch divided by 1 plus 1.08, and we get TFE is 2,404 pound-inch. So we get the torque on the iron core. Then we said the maximum stress for the iron core would be TC over J. The T from previous we got 2,404. CIN would be 0.6 inch and J would be half pi radius to the power 4, and you get the answer. Okay. And finally, angle of twist. We said angle of twist for copper, Cu and iron would be the same. Okay, and it would be, let's use for the iron TLJG. T from previous is 2,404. L we said is 6 foot, 6 times 12 inch per foot, and then J is half pi radius to the power of 4, and G is 11.2 times 10 to the power of 6 pound per inch square. And as a result, pound force cancel, inch square in the numerator, inch 4 inch minus 2 in the denominator cancel. We got the angle of twist for iron core, which is the same for would be the same for the copper shell. Okay. Homework 3.7. Determine the maximum shearing stress in a solid shaft of 10 mm diameter and it transmits 2.4 kilowatt or 2,400 watt at a frequency of 30 Hz and 60 Hz. Okay, so from what we learned, tau max, maximum shearing stress would be Tc over J for a solid shaft. And what is T? If we know the power, then the torque would be P over 2 pi F, because 2 pi Ft equals power. Okay, and then C we put it here. J is for cylindrical shaft solid would be half pi C to the power of 4, and simplify we would get P in the numerator, pi square, F keep, 2.5 cancel, C cancel, numerator and denominator cancel, C to the power of 3. Okay, then when frequency is 30 Hertz, the tau max would be P 2400 watt, which is Newton meter per second, pi square, F 30 Hertz or 30 per second, and C radius to the power of 3. 10 millimeter diameter radius would be 5 millimeter or 0.005 meter, and you get the answer. Similarly, when frequency is 60 Hertz, everything would be the same except the frequency would be 60 per second, and you get the other answer. Okay. Finally, homework 3.8, we say two solid shafts E, F, and I, J. Each of them are connected to gears. IJ is connected to gear H with radius of 5 inch, and EF is connected to gear G with radius of 3 inch. Okay, and the gear set is used to transmit 16 horsepower from motor at E, which means at E we have a motor with a 16 horsepower, and this power is transferred through the gear and shaft, and the motor is rotating at 1200 RPM or 20 Hertz, and this power is transferred to machine 2 at J at the other side. If the two are the same, we want to calculate the required radius for shaft EF, and for shaft IJ respectively. Okay, so go back to our same old equation for maximum shearing stress. For shaft EF, we know the maximum shearing stress has to be smaller than this value, 7,500 psi or 7.5 ksi. And what is maximum shearing stress? It would be Tc over J. And if we know the power, the torque would be power over 2 pi F, and C and J we keep. Okay, and if we expand the J, it would be half pi C to the power of 4, and simplify, we would get P over pi square F C to the power of 3, smaller than this value. And of course, the radius for EF would be, P divided by pi square F, 7.5 ksi become denominator, and this whole thing to the power of 1 over 3. You plug the number in, P 16 horsepower, and 1 horsepower is 6,600 pound-inch per second. Okay, pi square F is 20 Hertz, 20 per second, and 7,500 pound per square inch. Okay, pound and pound cancel. 1 over second cancel. Inch to the power of -2, inch to the power of 3, 1/3 inch. So we get the minimum radius for the EF shaft. Similarly, for shaft IJ, we have the same relationship. Maximum shearing stress will be Tc over J, and you simplify, equals to P over pi square F radius to the power of 3. It has to be smaller than 7.5. P would be the same because you are using the shaft to transfer as neglecting the loss. The same power would applied at E would be transferred to at J. So P would be the same. C you are. That's what we want. The only thing unknown is frequency for the IJ. For gear connection, hopefully in statics you still remember the gear H and J, they would have the same linear velocity, or put another way, the frequency ratio would be inversely proportional to the radius ratio. IJ is connected to H, and the frequency for H is the same for IJ, and frequency for H times RH equals to frequency for EF or G times RG. Okay, as a result, frequency for IJ would be frequency for EF times a ratio. That ratio is the radius for G gear divided by radius for H gear. Okay, and frequency for EF we said is 20 Hz, and RG, the radius for G is 3, radius for H would be 5, and now you see for IJ, because it's connected to a larger radius gear, its frequency would be slightly lower. 20 Hz times 3/5, it would be 12 Hz than the frequency at E. That makes sense because it connected a larger gear, lower frequency, smaller gear, higher frequency. Okay. As a result, the Cij would be the same P over pi square F over 7.5 KSI, the whole thing to the power of 1 over 3. And you plug the number in, you get the answer. Okay? Thank you.